All right, so let's talk about velocity and acceleration on vector functions. All right, so this is actually going to be pretty simple for you because if you have taken physics 1, and I know all of you have, then this is basically the same idea. All right, so as we know from physics, right, velocity can be broken down into its x and y components, and this is basically what this is saying. So velocity would be the same thing as the derivative of function r, but it's also you can split that up into the derivative and this is the velocity in the x direction. This is the velocity in the y direction. Okay. Acceleration, the same idea, and distance is the integral of the square root of the velocity in the x direction square, and this is the y direction velocity in the y direction square also. So let's just go ahead and go on to some problems. And right here is just giving you the definition of a limit, basically, or excuse me, of a derivative. And you can see that in this case, right, instead of you have a point here, and RT plus delta t is this point. So basically, when you make that delta t approach zero, meaning the difference between this distance and that distance becomes almost nothing, then you have what's called a derivative, right? So let's talk about real quick about how to do this. And again, you're going to find this for the most part pretty easily, or you're going to find it pretty easy, excuse me. So let's take a look, right? So in example 1, an object moves along the plane curve C described by the following function. All right, so mostly in calculus, AB particularly, we normally tend to deal with stuff in one direction for the most part. All right, but when we're trying to find the rectangular equation that describes the object motion, all we have to do, just like we've done before with a parametric equation, is we know, for example, that this right here is the x component and this is the y component. So I can write that x is equal to 3 cosine of t, and y is equal to 2 sine of t. Okay. And then in order for me to write this as a rectangular equation, what I can do, like I've done in the past, is I can square both sides here. I can square the x, I can square the y. Okay. And that's going to leave us with x squared is equal to 9 cosine squared t. And this will be y squared is equal to 4 sine square of t. Now, if we know that y square, cosine squared t plus sine squared t is equal to 1. All right, so as you can see, if I divide that x squared by 9 and I divide that y squared by 4, then that leaves us with cosine squared is the same thing as x squared over 9, and sine squared is the same thing as y squared over 4, and this is equal to 1. So this is the rectangular form of it, okay? Now to find the velocity vector, all right, so let's do one at a time. The velocity vector, all I have to do is take the derivative of my function r. So r prime of t would be derivative of cosine is negative sine. Derivative of sine is positive cosine. But notice how I'm writing this, right? The velocity vector, well, still a vector, so make sure we have the x component and y component. Now, that's the first part. Now, we'll also want to find the speed, right? And the speed is defined as the magnitude of the vector, of the velocity vector, excuse me. So all I would have to do for this, okay, and this makes a whole lot of sense. Like, for example, not really sure what this looks like, but essentially what I would have is I have the x component, which I can call like x prime, and this is y prime. And the speed is regardless of direction. The speed would be basically this part up here. This would be x prime plus y prime. So that's sort of where that's coming from. Well, all of that squared. Okay, so that's basically the formula for the speed comes from. So anyways, so it's going to be the speed in the x direction squared, the square root of all that, of course, plus 2, and I forgot to put the t here, 2 cosine of t squared. And in this case, it's going to give me a function back. Of course, if they ask you for the speed at a certain time, all right, then you could just basically plug in whatever number they give you for t and get a scalar answer. All right, so that's that for that. Then finally it's asking for the acceleration vector. Well, the acceleration vector, I know, is the derivative of the velocity or the second derivative of function r. So the derivative of -3 sine would be -3 cosine of t I. The derivative of 2 cosine of t would be -2 sine of tj. And that's the answer for that. So that's it for that part. Now, when we're sketching the graph, we know it's going to be a circle, but even if you don't know that, what you could do is I'm gonna write it over here because you're going to see I'm going to need this anyway. What you can do is you can always write your t value, and then you can write your x and y. And don't make the t's negatives, just start with 0. Okay, so if t is equal to 0, then according to this problem, right, if I would go all the way back to this, and I know what this is going to look like because I have this equation, but let's say that I didn't know that. If I go back all the way to this, if I plug in a 0 here, that's going to give me 1, so that's going to be 3, and that's going to be 0. So this would be 3, 0. And of course, I can pick 1, but, I don't really know what the cosine of 1 is and the sine of 1 is. I wouldn't know that. So the next logical one to pick would be like pi over 2. All right, and then at pi over 2, then the cosine would be 0, and the sine would be 1, which would be, in this case, like that. And I would go to pi, and that would give me -3 and 0. And remember, I'm plugging this back into the function r. And then finally, I could pick 3 pi over 2, and that's going to give me 0 and -2. So I kind of know at least what direction I'm going, right? I have 3, then if I plug in pi over 2, which is right here, that's 2, and then it's -3, and then 2 again. So essentially, I have an ellipse. And I actually start here on 3, right? Because when t is equal to 0, that's my starting point, and I'm basically going in that direction. Woo, I almost overshot it. So this arrows just indicate essentially where the particle is at a specific time. All right, so now they want to sketch the velocity and acceleration at 3, 0. So I noticed that at 3, 0, all right, which I'm going to write this in a different color here. At 3, 0, which is right here, t is equal to 0, okay? So first, I'm going to take have I already taken the derivative? Yep. I already know that this is my velocity here, so I can write that. So r prime of 0, okay? Again, I'm plugging in 0 because at x coordinate 3 and y coordinate 0, t is 0. Okay, so that's another good reason why you want to write that table. All right, so we have 0, so the velocity function was this. So that's just going to give me 0i plus 2j. Oops. All right, so this is how you would actually sketch the velocity on this. Okay, first I'm going to go to 0.30, which is right here. All right, so that's where I'm going to begin. And notice that the vector says 0i 2j. So from here, from 3, 0, I'm going to go 0 units to the right, and I'm going to go 2 units up, which is right here. All right, so again, this is the velocity at 0, at t is equal to 0. Okay. Now, for the acceleration, which is the second derivative, and again, I have to plug in a 0. Let's see, that will be negative 3 cosine of 0 I plus, and you know what? I'm gonna write it the same. I'm just gonna use a different color. I want to get fancy on this. So again, this is the acceleration, which is the second derivative of function r. So this is 3, and again, I already have that written over here. Okay, so you can kind of see it at the top of the screen now. All right, so as you can see on this one, that's just going to leave me with negative 3i plus 0j. All right, so let's go to coordinate 3, 0, which again is right here. Let's put our point there. And I'm going to go negative 3 units to the left from here, which is right here. And I'm not going to go up or down at all. So this is my acceleration vector at t is equal to 0. Okay. All right, so let's go ahead and move on. Now, on this other one, kind of the same idea. First, I want us to sketch the particle. Yeah, you could try to kind of solve this and find a rectangular equation, but we don't have to, okay? It's easier sometimes if you just don't do that. So what I suggest you doing is do what I did earlier and then write me a table starting with t is equal to 0. Remember, do not make t negative because t time cannot be negative, all right? So we start off with 0. Now, if we plug in 0 into the original equation, that's going to give us 4 for the x-coordinate, and it's going to give us 0 for the y-coordinate. And we just need a few. So let's see, if I plug in a 1, that's going to give me a 3 for the x-coordinate and a 1 for the y-coordinate. If I plug in a 2, that's going to give me a 0 here, and that's going to give me a 2 here. And then finally, if I pick a 3, that's going to be 4 minus 9, which is going to be a negative 5. And this is going to be a 3. Okay? So let's put those points. Remember, starting with 4, 0, which is right here. And then 3, 1. And then 0, 2. So I can kind of tell this is a square root function just because of where the points are located. And then finally we have negative 5, 3, which is all the way to here. So notice that I started with 4, 0, right? So my function is actually going in this direction. All right, so let me try to draw it as accurately as possible first. It's actually kind of hard to draw on the screen, but anyway. So what I'm saying is, yes, you do have to draw those arrows because that indicates the direction or the points where the particle is located at certain times. All right, so now that we have sketched this, they want us to find the velocity and acceleration at t is equal to 1. So in essence, that does make it a little bit easier because they tell me what t is. But sometimes they tell me what the x and y component are. Basically, they tell me the location. All right, and when they tell me the location, I have to look at the table and find out where it's at. But anyway, so let's go ahead and figure out the velocity. So r prime velocity is equal to r prime of t. R prime is going to be negative 2ti plus the derivative of t is 1, so this is just plus j. Okay. So the velocity at 1 is going to be negative 2i, well, plus j. That's not really going to change much. All right, let's figure out acceleration. Remember, acceleration would be the second derivative of function r. So the derivative of negative 2t is just negative 2i. The derivative of 1j is just 0j. So therefore, the acceleration of 1, it's not going to change anything. That's actually going to be exactly the same vector here, which I can just write as negative 2i. All right, so this is about the only part you have to be careful. Now, at t is equal to 1, that's actually located t is equal to 1 is located at 3, 1. All right, so whenever I draw my velocity vector, I have to draw that on 3, 1. All right, so start here for my velocity. And the vector, this vector right here, says that I need to go 2 to the left, so -2, and up 1 for j. So basically I didn't do such a good job drawing it. I'm not really sure. I'm supposed to go below the black line right there. I'm really supposed to go above it. That's almost like a tangent line there. But anyway, that's okay. You get the idea. Now for the acceleration, all right, remember, we're still going to do this 0.31. So at 3,1, my acceleration is just -2i. So that's just going to be right here. It's going to be a vector of length or of magnitude 2. It's going to be to the left. So this is A1, and this was V1. And that's it for that, guys. So let's go ahead and move on now. So let's go to example 3. Let me switch to black pen again. I think more or less this is going to be... Oh, yeah, this is actually a good question, I thought. All right, so the one is to write the equation of a tangent line. All right, so we know the two things that we need for a tangent line is a point, meaning an x and y coordinate, okay, and I need a slope, which is the derivative. So first, notice that it asked me at t is equal to 1. All right, so this is what we're going to do here. So we're not going to do a lot of changes here. At t is equal to 1, I'm just going to plug in a 1 for t, which will give me this. And I'm going to choose to write the vector like that, but you can still write it as 5i minus 11j. Doesn't matter. Okay, so here's the derivative then. And by the way, also, a good thing to note here is that this is actually a coordinate on the graph. Okay, so even though I wrote this as a vector form, this is actually a coordinate on the graph. Okay, so moving on. So now I have my point. Now I need to know the derivative at t is equal to 1. So first I take the derivative of r, which is going to be 6t squared plus 6ti plus 2t minus 12j. And then I'm going to plug in a 1 because I need to know the derivative of 1, right? And that's going to give me 12i minus 10j. Now, I need to find this, okay? So if you think about what we just found, this right here is dx dt. And this right here is dy dt. Now, we know from the parametric function stuff that dy dx is the same thing as having dy over dt over dx over dt. So what I'm trying to say is that what I'm going to have is -10 over 12, which is going to be -5 over 6. Okay? So again, at t is equal to 1, at that specific moment, the particle is located at 5, -11. So this is actually the coordinate point. And the velocity at t is equal to 1, the velocity with respect to x, essentially, not with respect to time, is -5 over 6. So that's how you draw the line right there. All right, so that's the equation of a tangent line. So we're going to leave it there. We're done with that. All right, on B, we're going to find the coordinates of each point. The horizontal component, the velocity is 0. Notice this says the horizontal component. The horizontal component is this one right here. So if I want to know what the horizontal component's velocity is 0, that means that I have to look at only the horizontal component of the velocity, which is this right here. So I can write, I just want to know where this horizontal component of the velocity is equal to 0. So really all I'm doing is just setting that equal to 0. Now notice that it says that assume that t is greater than or equal to 0. Okay? So basically solve for t. So we can factor out a 6t here. So that's going to leave us with t plus 1. All right, so 6t is equal to 0. Set each factor equal to 0. Long story short, this is t is equal to 0 and t is equal to negative 1, which I cannot have because that's a negative. All right, so we're going to say, and also remember it says assume that t is greater than 0, right? Normally on this type of problems, we're assuming that t is time. Okay, so now, there it is. There's only one question, all right? So, and it says find the coordinates of each point where the horizontal component, right? So we want to find the coordinates, all right? So what that means is I'm going to plug in that back into the function, into function r, which in this case, if I plug that in, that's going to give me 0, 0, which means I'm at the origin. So basically, when I put a time into the position function, that's going to give me the position of the particle at a certain time. Okay. All right. So now finding the position function. Now on this one right here, let me see how I did this here. Okay. So I'm going to show you a couple of. Well, actually, I'm going to show you one way to do it, but I'll at least tell you how another way you could do it as I'm doing it. So notice that I have the acceleration function, and we want to find the position vector. Okay, we do want to find that, and then find the position at t is equal to 3. I wish I hadn't say find the position vector because I really don't want to do it like that. But anyway, here's what we do. We're going to take the integral. We know the velocity is the antiderivative of the acceleration. Let me see if they do this again. No, they didn't do it again. But anyway, so let's just take the antiderivative of this. So this is negative sine t plus, we're going to call this c1. We're going to have to find those c values, so don't combine them, okay? If this is just a straight up indefinite integral, then sure. Now the antiderivative of sine is negative cosine, so that's going to give me a plus cosine of t minus 1. Excuse me, t plus c. I think I jumped the gun on that one. I was looking at my notes. So we're going to call this C2J. All right, notice that now they tell you that V naught is equal to 2I. All right, so that's kind of an important deal here because what I just found there, this is V of t right here. So at V naught, we have 2I. Okay, so what that means for you is if I plug in a 0 here, that's going to give me 0. So I have C1 is equal to 2. So we're just going to match them up. Okay, so that's that one. Now if I plug in a 0 here, that's going to give me a 1. So I have 1 plus C2 J is going to be equal to the J component at 0. But I don't have 1. So what that means is that this is 0. So therefore C2 is negative 1. Okay. So V of t is equal to negative sine of t plus 2I plus cosine of t minus 1j. Okay, so now we're going to do that all over again. All right, so we're going to take the antiderivative. I know that my position function called r of t here is going to be equal to the integral of negative sine of t plus 2 plus cosine of t minus 1 j dt. All right. So I'm going to take the antiderivative of that. So the antiderivative of negative sine will be positive cosine plus 2t. We can call this C3i. Now this one right here, the antiderivative of cosine, it's negative sine. Oh, wait a minute. Is that right? Antiderivative of cosine. No. I don't think that's it. Yeah, okay, so I'm good. The derivative of cosine is negative sine. Yeah, the derivative of sine is positive. Okay, so we're good here. Okay, so basically I'm doing the same thing and then on the last one, all right? So r of 0. I'm going to write it like this time. I'm going to call this 0i to avoid confusion plus 1j. That's basically what they said here. Same thing, right? So essentially we're doing the same thing. If I plug in a 0 into the I component, I have cosine of 0, which is 1. 2 times t is 0, plus c3 is going to be equal to 0 to my 0 function, or excuse me, 0 for I. So therefore c3 is going to be equal to negative 1. Okay. And then now, let's see what else we got here. This right here, let's see, the sine of 0 would be 0 minus 0 plus c4 is equal to 1. So c4 is equal to 1. Okay? So my position function, therefore, would be r of t is equal to cosine t plus 2t minus 1 I plus, let's see, sine of t minus t plus 1. Yep. J. And finally, at the end, they want another position at r is equal to 3. Okay, so r is equal to 3. Basically, I would have the cosine, and you're going to have to plug this in your calculator. This would be 6. This would be 1. Remember, this is going to be a vector. And this right here would be sine of 3 minus 3 plus 1. Let me put that in the calculator real fast and see what I get. Let me pause this for a second so you don't have to hear me type this in. All right, so after plugging that in, that is what I have. Okay, that is the right answer. There is an alternate way. So on this one, I kind of couldn't do it the way that I wanted to because this one actually asked me for the position. They asked me to find the position vector. But had they not asked me for the position vector and then just asked me to find the position at t is equal to 3, I could have done this alternate way where I know the antiderivative of velocity between 0 and 3. And again, the reason I'm even doing this is because that actually kind of becomes sort of a big deal on the test. It comes up a lot. I can do the fundamental theorem of calculus. Again, I'm not doing anything crazy, right? The antiderivative velocity, we know that's the position function r. So r of 3 minus r of 0. Now, because I'm looking for R of 3, I'm going to add R of 0 to this side, to the left side. So essentially, you could do the problem like that, where R of 0, we know that that's like basically, well, let me write it like this. It's J or 0i plus 1j, however you want to call it, plus whatever integral you get from here. So essentially, I like to do it like this because I feel like I do less work. Okay, but whatever you get for this integral, which is very similar to what we got here. Okay, except for in that problem, we're just actually plugging in those values. Then that essentially gives you the same answer as what I got. But again, I do want you to remember that at some point because we're going to use it a lot. All right, so let's go ahead and move on to projectile motion. So in pre-calculus, we solve vertical motions using position function. So now we normally would do only one, what do you call it? We would only talk about motion in one dimension, okay? But projectile motion, as what you have done already, is in two different dimensions. Obviously, you have the x component and the y component, just like the stuff we've been doing. So in essence, it's not that much different than what we talked about so far. Now, normally, right, this is the ROT. You would have to break this down into its x and y components. Now, I'm just going to tell you this right away, right? If I have a velocity and they call this v naught, all right, so that would be the velocity of whatever, a projectile, right? And they also have to give you an angle. Well, I have to break that into its x and y components. Now, the x component would be this. You can kind of see if I do SOHCAHTOA, that's what you would get. All right, so that would be the position of the projectile and the x direction, the position of the projectile in the y direction. Okay, now what I would do for this, right, because I have some sort of force acting on it, is that let's think about, and I'll do this real fast because I know you really probably don't care. Now, in the x direction, this doesn't belong there because we don't have the gravity does not act. That gravitational force does not act on the object and the x direction. It only acts on it on the y direction. So essentially, all you would have left over would be this, right? Which is the velocity in the x direction, if you don't know that, and projectile motion. As soon as the ball or the bullet leaves the gun, the velocity in the x direction is only controlled by this function right here. Okay. Now, in the y direction, notice that you have initial velocity, and you also have this, which is actually the gravitational force acting upon the object, and you have initial height. This one really should have also initial, even though it doesn't have it, this technically should have initial, like the initial, position in the x direction, although they don't write it, don't know why, but let's just go to example 5, all right? I'll stop complaining about this curriculum. All right, so first, they want to know a parametric equation of the cannon's ball trajectory. Well, that's basically what I just said. I want to break this down into x and y components, okay? So first, remember that in the x direction, this is the x direction, all I would have, let me change to black here. So we would have the initial velocity times the cosine of 60 degrees. That's the velocity, excuse me, that's not velocity. That is the position of, let me think about this before I said it. Oh yeah, I forgot the two, no wonder. So this is the trajectory in the x direction, all right? So that's going to track that for you. Now, the trajectory in the y direction will be given to you by this other part right here. By this part right here. Now, on this one, we're assuming the h naught, or the initial height, is 0. Okay, so we have initial times the sine of 60 times t minus, now because they want this in feet per second, the acceleration of gravity, maybe I should say that, the acceleration of gravity in feet per second squared is 32 feet per second squared, like this. Okay, so therefore that's why I'm going to write this as negative 1/2 of 32 is 16, so this is 16t squared. Okay, what else do we need to know here? If you just plug that into your calculator, you get 150 for this. And of course, you know, if we were actually doing this as a physics problem, I'd probably just get a decimal answer for that, for this one particularly. For the 150, probably not. All right, so those are the two functions. Now, I want to know the maximum height reached by the cannon. Now, we know that the maximum height is reached when the velocity in the y direction is equal to 0. I don't know if I want to call this Vy is equal to 0. All right, but essentially, I want to know the velocity in the y direction has to be equal to 0. So meaning, when is this part right here? Well, I guess first, I have to do two things. I have to take the derivative of y. All right, so I'm going to take the derivative of this right here. So it's just 150 squared to 3 minus the derivative of negative 16t would be negative 16t squared. Is this? Okay. And now I'm going to set the velocity in the y direction equal to 0 and solving it. Normally in physics 1, when you took it, they gave you the formula, so you didn't have to do the derivatives or anything. But what's the fun in that? So if you solve for it, again, you probably could get a decimal for this, but I didn't, so I'm not going to. Okay. And this would be in seconds. Now, this is the horizontal distance traveled by the cannon. All right. So what I know is that when the cannon hits the ground again, the height will be 0. Okay. So what's going to happen here is that I need to first figure out when the height is equal to 0, meaning when the y coordinate, which is this, when the trajectory of the ball in the y direction, need to figure out when this is 0. All right, so don't get lost. This is the equation of the trajectory of the cannonball. And the y direction. So anyways, if I set that equal to 0, I'm going to factor out a t. Set each factor equal to 0. So you have one time that t is equal to 0. You have another time where t is equal to 150 squared to 3 over 16, which is 75 squared to 3 over 8. Okay. And then now, after that, so that's the time that it takes for the ball to hit the ground. So since I want to know the horizontal distance traveled, I'm going to plug this into the x component, which is this one up here. Or I guess I can use that one, probably easier. So it'll be 150, and t is this ridiculous, well, let me write it like this. So yeah, it'd be like 150 times all of this ridiculous numbers. And that will give you approximately 2435. Let me check that real quick. Yeah, 2435.696 feet. All right. And then finally, the speed of the cannonball. All right, I have to know the velocity in the x direction and the y direction. So let's see, if r was this, and then notice this had impact. Well, if you knew anything about projectile motion, you know that the speed, assuming there's no air resistance, and you're in a vacuum, the speed at which the cannonball left the cannon, okay, is going to be the same speed as it reaches the same height. So basically, the answer, I already know the answer is going to be 300. But for the sake of what we're doing here, let's just go ahead and explain this, right? So this is the vector that describes the motion. And I would have to take the derivative, which is going to give me, put b prime, that's not what I meant. That'll be the derivative of this. This is 150i. And this is, let's see, 150 squared root of 3. So it's basically what I have on the last one, minus 32, or on part B, that is. Right now, at impact, I know that the ball hit the ground at this time, which I already wrote here. All right, so what I would have to do is remember the speed. The speed is the square root of the velocity in the x direction, which is 150 squared. That's it for that. And the velocity in the y direction, but I'm going to have to plug in that time that I have there, which is 75 squared root of 3 over 8. All of that crap squared. And when you put all that stuff, you should get 300. Feet per second, of course, because we're talking about speed here. All right, so the difference in speed, guys, is to notice that I don't have a direction for that. It just tells me the speed without the direction. So that's the difference, right? So it's just the magnitude of the vector. All right, guys, so that's it for that. Again, this is probably longer than it needed to be, but I felt like I needed to go through every example. All right, I think this lesson was so easy, even Rebecca could understand it, but we'll see.